Okay, so this is the first of multiple sort of like notebooks for the lab on Bayesian techniques, and I'm calling it the many faces of the Reverend Bayes because Bayes' theorem comes in so many different ways in machine learning, in statistics, that I thought I'd sort of illustrate some of the different ways it comes in. And so what I'm calling phase one is really where Bayes' theorem comes in the definition of things that go into machine learning, and where it comes into machine learning algorithms directly. So we're just going to set up some code here. The usual CV optimize, do classify, points plot and points plot probability to show probabilities. And without much ado, you've seen Bayes' theorem in class. Basically, it's saying the probability of a hypothesis given the data is equal to the probability of the data given the hypothesis times the probability of the hypothesis divided by the probability of the data, or what's also known as the likelihood times the prior divided by the evidence. This follows directly from the definition of conditional probability. It's not a very hard thing to see because if you multiply both sides by P of D, then this times this is equal to this times this is equal to the joint probability of D and H together. So here's something to try out during a section. I have a little example here. It's an example of cancer. And you have to figure out whether you have to do any further testing or go in for a biopsy or something of that sort. So I'm not going to give you the answer, but try and work it out in like 5 minutes or so in your section. Okay. So in machine learning, we've generally been talking about expectation values of functions, specifically expectation values of risk. But just to have the notation clear, I just wanted to write down the expectation value of a function f of x and y, where x is the features and y is the response. So if it's a regression, this is the features for the regression, and y is the continuous variable. If it's a classification, y can be the classes, C1, C2, C3, so on and so forth. So the expectation value with respect to x and y is basically the expectation value of the function of x and y with respect to the joint distribution. And I have that dx dy, which really shouldn't be there because I'm summing it over here. But just think of the sum and or the integral as the same thing. If it's continuous, think of it as an integral. If it's discrete, think of it as a sum. I'll fix that. So we're going to use a sum everywhere. So in the regression case where you have everything continuous, you might want to replace the sum by an integral. And so, for example, you can think about the risk of an action G at any given, so G, for example, could be an action as to what you should do if you have cancer. Maybe you go and get a surgery. Or it could be an action which is within the realm of the possibilities that classification allows you, whether you have cancer or you don't have cancer. Deciding whether you have cancer or whether you don't have cancer. So G is completely general. The risk of an action G is a loss that's encountered when you have y. When you took action g of x when the actual value is y, basically. And so you are weighting it, as you might expect, since this is an expectation, with the conditional probability of y given x. So at that x, what was the value of y? So what is the probability that for that set of features you had class 1, or for that set of features you had class 2? And you can see that these formulas are actually sort of like related to each other. If you want the expectation value over all the features of the risk, then basically you're gonna sort of do what you would think would be the sensible thing to do, which is to weight the risk at each point x by the probability at that point x. And you can write this out, and you can see that it basically gives you the same formula as up there. So this is just a little bit of algebra to show you that all these definitions are kind of identical. Okay. So given these definitions, what kind of losses do you use? For example, typically in a regression case, you use a squared loss, where G is the continuous action. It's basically choosing a point y, and you can use G minus y squared. By the way, this is not the only loss you can use for regression. You can use the absolute value loss as well. And for classification, you typically use the 1-0 loss, which is 1 when the two of them are not equal to each other. So this is all stuff you've seen before. There's none of this is new. You've done this in homework 3. You've used these various risks. You played around with it. I just wanted to sort of like set up the formalism here. Now, let's go back to sort of like the general notion of learning. And I drew this little diagram to basically show that the way we've talked about learning of algorithms right now, so there are two separate ways of doing it. One is what's called empirical risk minimization, where you just take all the samples and you minimize over that. And the other is to actually try and get a probabilistic model for it. And all these models, which are probabilistic models, actually turned out to be Bayesian in the sense that they have something or the other to do with Bayes' theorem. They're not necessarily Bayesian in the sense that you're setting priors and so on and so forth. But that is a, so this is what I mean by the phase one of the Reverend Bayes. They use Bayes' theorem to set themselves up, and there's a sort of like a probabilistic structure. And amongst those, there are two kinds of models. There are discriminative models like logistic regression, and then there are generative models like naive Bayes, like LDA, like Gaussian mixture models, and so on and so forth, which basically have kind of a story to them, and we'll just come to the difference between the two in a little bit. But one of the points to just remember from this diagram is that as you go down this, you have more and more modeling assumptions that you're trying to put into your model. So empirical risk minimization, you've seen this. Basically, you're just minimizing the loss at individual points, and you're dividing by the total number of points you have. And I have some text over here and some diagrams to kind of show what this is. I won't go into those in any particular detail. But I'll just point out that Vladimir Vapnik, who is the inventor of the SVM, and a big proponent of the empirical risk minimization way of doing things, says never solve a more difficult problem, which is density estimation, while solving a difficult one, which is the learning problem, which is already a difficult enough problem. Why are you solving a more difficult problem? And so it's kind of like a counterpoint to why are we doing all this Bayesian stuff in machine learning and so on and so forth. You should just do empirical risk minimization. And this is a photograph of him at the point he joined Facebook. But there are reasons why you want to do this. In many ways, especially if you don't have too much data, it seems crazy to assume that the empirical distribution is a good distribution. Especially for small data. In this day of big data, it might be a better assumption than it ever was. But big data is big in some dimensions. Sometimes it's small in others, and so on and so forth as well. So if you have more information about the problem domain, if you can make more reasonable assumptions for the distribution, then you can do actually a better job. There's a second reason you might want to do this. When you're doing empirical risk minimization, you're directly minimizing the loss over here. But if that loss changes over time, as it always does, for example, in financial applications, in risk applications, so on and so forth, then you're out of luck. You've got to do this all over again. The third reason to do this is that there is no way to associate, in this framework, there's no way to associate confidence intervals, except by resampling associated with this, which a probability distribution will kind of give you in a much, much more natural sort of fashion. So you might want to do it for that reason. So what's the idea in this kind of Bayes approach? I hesitate to sometimes call it a Bayesian approach, but I'd rather call it like a Bayes theorem-ish approach. The two ways that we talked about are discriminative. And in discriminative, what you're doing is basically you're taking the joint distribution of x and y. Here I've called it C, since let's just talk about classification for a second. You're directly modeling the probability of a class C given x. So you're directly modeling the probability of class 1 or probability of class 0 given the features x. In the generative approach, you're actually modeling the other thing. You're modeling the probability of x given C. You're modeling the class conditional probability over here. And as you know from Bayes' theorem, these two are equal to each other. So once I get this, I can always solve for this, which is eventually what I want to actually find is PC given x. I want to make a classification. So you can always solve for one from the other. But so these are two separate ways of doing it. So basically, what the generative approach is like, you pick a class with probability P of C, and having picked the class with probability P of C, you find the x belonging to C. You find the x that correspond to that C. So for example, in our usual example, which we'll go into in just a second, of the heights and weights of males and females, what you're doing in the discriminative way of doing it is you're basically directly saying what's the probability of male given the height and weights, what's the probability of female given the heights and weights. In the generative approach, what you're doing is you're saying, okay, I'm going to take out all the females from the data set. I'm just going to fit the males. And say, what's the probability of a height and weight given that it's a male? And then I'm going to take out all the males from the data set and keep only the females and say, what's the probability of the height and weight given the females And then I'm going to use Bayes' theorem to invert it and get this. And so that's the difference between these two processes. So again, I'll skip over these diagrams and go directly to the code. Again, it's the usual 0, 1 heights, weights thing. You've played with a discriminative model ad nauseum by now. It's a logistic regression model. You've seen this kind of diagram ad nauseum as well. And what this does is that it basically says, I'm not separating the males from the females. I am just straight away modeling for the probability of male given the data and female given the data. And the kind of contours that you get, these are the probability contours that you get from this model. And you can see that the probability contours from this model are these straight lines. And so basically what P of C given X is giving you is basically a kind of discrimination line. And that's why this is called a discriminative classifier. It's saying, what's the probability of C, red, given X? And that's what the contours are about. In a generative classifier, as I said, you're going to try and get the probability of height and weight given that it's a male. And you might assume from your kind of notion about weights and heights that given that it's a male, that the heights and weights of male have something to do with the normal distribution because various factors, genetics, nutrition, all of these kind of add up, and you wave your hands and you say normal distribution. So you say, okay, I'm going to model this using a normal distribution, and I'm going to do the same thing for the females. And when you do that, basically, you'll land up with linear discriminant analysis, which you can go read up on, and it's there in sklearn, and you can actually fit it. And when you fit it, you can see what you get out of it. I have a little bit of code to fit it here, which I won't go into in any detail, but this is what you get. So you're basically fitting a separate ellipse to each one of these data. That's a two-dimensional Gaussian. And what you've done over here, you made a specific assumption that you're tying the covariances of these things together. The specific assumption is not that particularly important, but it does have some consequences. But here you fitted one ellipse for the males and one ellipse for the females, and you said, okay, these ellipses are now going to give me probability contours, right? I mean, the probability contours are probability distributions. So there's some two-dimensional normal distribution sitting here, and there's some two-dimensional normal distribution sitting here. And there's going to be a place where these normal distributions meet, and where one goes below the other, and that's the place where you're going to make your decision. Where one probability is higher than the other, it's a male or a female. And when you do that, you get exactly the same probability contours. So this is done by actually saying which one is higher than the other. And so what happens actually is that every generative model typically has a discriminative model as its counterpart. What you're doing is you're trying to actually get P of X given C. But once you get a P of X given C and you write out the formula for P of X given C as this two-dimensional normal distribution and so on and so forth, and then you solve for P of C given X, it turns out that the answer you get for solving for P of C given X is exactly the same answer as a logistic regression. And this is actually true of many models. It's not just true of linear discriminant analysis. Models with Poisson likelihoods and naive Bayes models, which are also generative models, also have logistic regression as their discriminant, as their discriminative counterpart. The deal here is that indeed, if somehow or the other the Lord came and actually told you that the P of X given Y is indeed a normal distribution, i.e. the probability of the heights and weights given that you're a male or a female is indeed a normal distribution, there is no classifier that will actually be better than linear discriminant analysis. If you have actually modeled your domain in a good fashion, you can always do better with a generative classifier. So LDA is what's known as asymptotically efficient, which means that for large amounts of training data, you can actually prove that no model is going to be better than LDA for this particular situation. Okay. So one last thing about generative classifiers is that because you have P of X given Y, or P of X given C, right, you can multiply it by the P of C and then add over all of them using the product and some rules of probability, and that just gives you P of X. And because you can do this and you get P of X out of this whole thing, you can actually get the distribution of the features. So in this sense, actually, generative classifier is asking you to do much more, right? Basically, it's basically saying, I want you to give me this distribution, right? And this distribution took a lot of modeling. It said, oh, I needed to know this domain that that the heights and weights of males, they look like a normal distribution because of these various blah, 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 right? And you came up with all of that. And what you can get out of it is that you can actually now, because you did the modeling for both the males and the females, just sum it up together and get the entire distribution of heights and weights. And so you actually get a very good characterization of the data set. And next week, we'll actually invert this question and ask, what if I actually don't have any males and females? I don't know that there are males and females in this data set. Could I have figured this out, that there were males and females in this data set? Or was it males and females and Martians in the data set? Right? So we don't know that. If we didn't know that, how would we figure that out? And when we do that, we sort of do that in terms, we take the P of X and we write it in terms of Y. And here the Y's are not necessarily classes. They're just some kind of latent thing. You've been seeing these latent models recently in the recommendation homework, So you have some idea of these. These are some things you think have some grounding in reality, but might not. But you can calculate P of X in this particular fashion using these latent classes. And in the cases of things like k-means and so on and so forth, they may actually correspond to clusters of things. So, but that's for next time. Okay. So let's move on a little bit on to naive Bayes. And naive Bayes is basically a kind of classifier which directly uses Bayes' theorem to make very, very simple classifications. And let me sort of show you what that looks like. So here's the probabilities written out in some amount of detail. If I want the probability of y being the class C1 given x, I can, in the generative scheme of things, I can model P of x given y, multiplied by the class prior, the probability of y given C1, and then divide out by both those things. Notice, by the way, that whenever you see a formula for Bayes' theorem, so something that I always remember is that whatever is in the second part over here, y is equal to C1, y is equal to C1, must be repeated in the denominator, and plus you add the same thing, analogous thing for the other classes. That's the way I remember how to write this formula. It's kind of works for me. But you get the idea. I mean, you're just dividing by all the possibilities here. This is essentially just P of x. Okay. So, and then you go P of x multiplying that side, and you get the two sides of the conditional probability formula. So what we're going to do over here in naive Bayes is to make a really, really, really somewhat ridiculous assumption that P of x given C, x given any of the classes here, like so here C1 for example, just multiplies into the probability of x1 given C and x2 given C and x3 given C. Now a place where these classifiers are used, these kind of naive Bayes classifiers are used a lot is spam classification. And if you can convince yourself that in the context of spam classification that this is a rather ridiculous assumption. This is basically saying that if I had the words sex and Viagra in one document, that the probability of sex being in the document is multiplied by the probability of Viagra being in the document. Now, you probably realize that this is a kind of stupid assumption, because if one is there, it's very likely the other is going to be there in any of the spams that you might have seen. But it's an assumption we're going to make. And it actually turns out to work really well for reasons we'll come to in a second. But you should know that it's a somewhat perplexing and somewhat ridiculous and somewhat preposterous, actually, assumption that you're going to make. Well, let me backtrack a little bit. Naive Bayes is not just used to do like spam classification and so on and so forth. It's used anywhere where you might actually expect causes to be somewhat independent of each other. So disease modeling is a place where naive Bayes is used in a lot of different fashions. So if you want to predict if somebody has diabetes, right, you could just like write down a very simple model in which the causal directions are the directions of the arrows, which says that diabetes causes insulin, diabetes causes glucose, diabetes causes mass, diabetes causes pregnancy, and diabetes causes age, which sound entirely ridiculous and is entirely ridiculous. Really, the causal arrows in these are probably in the other direction. But sure, diabetes causes a stronger insulin response and so on and so forth. So this graph isn't actually right in terms of its causality. But what it is right is in terms of saying that Yes, there is going to be some confounding between pregnancy and age, and pregnancy and mass and age, and so on and so forth. But in general, let's just assume that the probability of of age given diabetes is multiplied by the probability of pregnancy given diabetes, multiplied by the probability of mass given diabetes, this and this. All 5 of them multiplied together give you the joint probability. So in either this is the conditional independence assumption that is up there. And that's why this kind of works well in diseases, because you do different tests. And you say, okay, well, the outcome of this test and the outcome of this test, the joint probability of those two is equal to the probability of the outcome of this test multiplied by the outcome of that test, multiplied by the probability of the outcome of that test. Okay, so let's do this. So this is a old data set on diabetes amongst Pima Indians, and 1 is for diabetic and 0 is for not diabetic. So we'll set up a very simple Gaussian naive-Bayes classifier using these predictors. Pregnancy, your body mass index, your diabetes pedigree, which means whether your parents had diabetes or not, your age, your glucose concentration, and your insulin. And you can see those last 2 are results of tests, actually. And we'll set up a naive-Bayes classifier, but we'll set up what's called a Gaussian naive-Bayes classifier. I'll come to that in a second. And we'll do the train and test split, and we'll fit on the training, and we'll predict on the test. I'm not doing any cross-validation. I'm not doing any parameters. I'm doing none of that stuff right now. Just to illustrate what's going on. And you can see that this classifier does actually somewhat reasonably. It's not great. I mean, it's 140 correct and about like 50 wrong. But it's a reasonable classifier. And that's it. That's actually all there is to naive Bayes. And what that is essentially doing is it's basically implementing this formula for you, and then taking this thing and splitting it up into these different probabilities. And so here's the thing. So naive Bayes is a good assumption for things like multiple tests in the cancer example. A biopsy is conditionally independent of a blood test given cancer. So it sort of works surprisingly well in the medical field. When you talk about a generative model, so one way to think about this is that this is the way, if you're talking about documentations for docs, if you're trying to write spam, basically. So what you're going to do is you're going to have a vocabulary of words, which has words which are both in regular emails and words which are in spam. Then for each word, what you're going to do is you're going to flip a biased coin. And with that probability, that word's going to be in that document. That's your next step. So now, if you are in a spam thing, then the spam words will be more common in that particular document. If this is a regular email, then the regular words will be more common in it. So this is the way you're assuming that the document was written, which is kind of like, again, a kind of preposterous way to write any piece of text. You would not write a novel in this fashion. But that's the statistical model for the writing of this email, whether it's a spam email or a ham email. Okay. So for text classification, naive Bayes does much better than decision trees, as it turns out. And as I said, again, this is preposterous because you're throwing out all meaning. You're basically treating the document as a bag of words, essentially. So you're throwing all meaning out of the window. The only one that actually beats it for in the modern day for text classification is the SVM, and it's SVM with the linear kernel. So it's actually quite fast. So if you're working with text data, try the naive Bayes first, and then try an SVM with the linear kernel, and you'll probably get good results. And as a rule of thumb, on any machine learning problem, try k-nearest neighbors if it's small enough. K-nearest neighbors is problematic when it becomes very large numbers. And naive Bayes on any problem first. And they'll be simple, and at the very least, they'll set up a baseline classifier to you to compare your handy-dandy, super-duper random forest classifiers and everything against. So you probably realize that if I do this, and I go look at this particular formula, that even if one of these was 0, then it wipes out my probability over here. So if I'm looking at sort of like some set of words which are in a document, and say that document is supposed to be spam, so X is just some set of words, and C is either spam or ham. Let's say it's spam for the sake of argument. Then the probability that there is this particular word, let's say the word is supercalifragilistic, in the probability of supercalifragilistic in spam is 0. Then you're going to get no estimate out of this. This is a problem with naive Bayes classifiers. So what you do is basically you go into a seance and you start hallucinating, and you just hallucinate an estimate of 1. Even though the probability is 0, you say I have 1 out of n where n is the number of spam documents here. 1 out of n is the probability of getting the word supercalifragilistic in there. And that's what you do if there is a 0. So what you typically do is you start with the maximum likelihood estimate, and why it is a maximum likelihood estimate you can read about in more detail in more theoretical stuff on naive Bayes. It's basically the number of attributes in that spam class, the number of documents which have that attribute, the number of documents which have supercalifragilistic in the spam divided by the total number of documents in the spam class. And even if this is kind of small, what you can typically tend to do is that you basically do some kind of regularization of this probability estimate. Because by now we know that whenever we have very small numbers, we don't trust them very much, and we want to regularize them as being something more towards the mean. And so that's what we do over there. Okay. And you can justify this mathematically using higher level priors on these probabilities. So, and then finally, when we actually do these calculations, and if you go and look at the source code for naive Bayes in scikit-learn, you can see this, is that you actually use logs, basically. You never typically do in any of your work that you'll ever do when you multiply lots and lots of little probabilities, never do that. Do sums of logs instead. Because you'll get underflow floating point errors. When you do sampling, if you're going to take AM207, you'll have exactly the same deal. You'll do sampling for logs of probabilities, not for probabilities themselves, because of the floating point issue. Okay, so that's naive Bayes. And there's a very important thing that we haven't talked about yet about our classifiers. And this is not just true for naive Bayes, but it's also true for any classifier which kind of gives a probability estimate. And that is whether your classifier is well calibrated. So what is this notion of calibration? So calibration is basically this idea that how good are the probabilities that this classifier is giving you? So if you remember, what happened in naive Bayes is we made some rather preposterous assumptions. As I was giving you the example of the word sex and Viagra in a spam, we said that the probability of of sex and Viagra in a spam is equal to the probability of sex in the spam and times the probability of Viagra in the spam. And this was kind of like a weird sort of assumption to kind of make. Now the deal with this is that because of this, the probabilities that you actually get from a naive Bayes classifier are not actually quite accurate. On the other hand, what is correct about the probabilities you get from a naive Bayes classifier is that they are relatively ordered in the same fashion. So for example, if a document was more likely to be spam, right, than a document that was less likely to be spam, having these probabilities multiply actually goes in that direction and makes it more likely to be spam. In fact, it overstates the situation. So if you see any of these calibration plots in naive Bayes, you get calibration plots that look something like this. And what I'm plotting out here is the probability that the classifier gives versus the empirical fraction. So what I'm doing is I'm taking bins. I'm saying let me take everything which is of probability between 0.9 and 1. And let me see how many actually had that kind of the probability in the data set, just by looking at the frequencies of those things in the actual data set. So I can do that on the training set, and I can do that on the test set, and you'll always get this kind of structure in a naive Bayes classifier. This is the 45-degree line, and it kind of goes like this, basically. So which is what it's telling you is that around here, in the high probability region, that the naive Bayes classifier is actually a little bit more optimistic. It's saying that the classifier given probability is actually kind of higher than the empirical fraction. So you're getting a 0.8 probability when the empirical fraction is about 0.6. And over here, it's actually it kind of undersells it a little bit. But the ordering remains the same as you would have with a perfectly calibrated classifier. So logistic regression, on the other hand, for example, actually gives you much better calibration of probabilities. In fact, discriminative classifiers in general do slightly better on giving you the calibration of probabilities than generative models tend to do. But it's important to look at these kind of plots whenever you do any classifier which has probabilities, and we haven't done that so far in this class as yet. But naive Bayes is a very good example of where to do it, and when you do a naive Bayes with the text, as we shall do in the next lab, you'll see an example of this coming in. The other thing we actually do on the classifier probability is we actually do a against the probability the classifier gives, we give the number of samples which are there. So this is basically saying that a lot of naive Bayes classifiers have this because of this structure over here, have this sort of like boat-like structure in this histogram, where they predict a lot of things as spam very strongly and a lot of things as ham very strongly, and not much in between, because this multiplication of these probabilities push you to these extremes, essentially. So this is kind of like telltale of a naive-Bayes classifier, and the logistic regression classifier will do a much better job on its calibration. Okay, so I won't go into the code basically on how to make this calibration thing. You can read it, but basically it's cutting stuff into bins, and it's comparing the bins by the probabilities given by the classifier, and it's showing you how many samples are there. Really simple. You just count how many things in the classifier on the test set gives you stuff between 0.5 and 0.6. And then you plot that against 0.5, for example. Okay. So a little bit of redux on generative versus discriminative here, which might actually be kind of useful. So if you only want to make classification decisions, like is this a 1 or is this a 0, a discriminative classifier is cheaper in terms of computing resources. It's less work. It's less modeling. Use it. The moment you want to do something more complex, like asymmetry or some bizarre utility curve or something, you know, and so on and so forth, then you should use a generative model, because it's kind of independent of whatever risk you put into it, risk you put in later, essentially. The other thing about the generative model is there is a story by which you're making data in this model. As we told you in this document, you're throwing this biased coin. You're saying, okay, this is spam, and now we're going to throw a biased coin for the words in it, given that it's spam. So we are basically generating stuff essentially from P of x given C. C, spam. What's the probability of x given C? Okay, the probability of Viagra given spam is 0.8. Okay, so let's flip a coin for the word Viagra. Maybe it came out 0, but 8 out of 10 times it'll come a 1. Put the Viagra in there. Go to the next word, next slot. Next slot is supercalifragilistic. Probability in spam, 1/10. Flip a coin. Not very likely to show up heads. Okay, supercalifragilistic is not there. Go on to the next word, and so on and so forth. So that's a generative process by which the document is made. So in the example of the heights and weights, basically what you're doing is you're having these two ellipses, and what you're saying is, okay, there's a certain probability of being a male and a certain probability of being a female in this data set. Maybe there's 55% males and 65% females. Flip a coin. Oops, it's a male. Okay, here's a male. Draw a sample from the distribution, from the 2D normal distribution. Boom. That's where the sample is. That's the height and weight of that male. So I can generate data using this. So basically, generative models allow me to generate new quote unquote, I don't know exactly what I call it, but I guess fake data, so that I can run simulations on the fake data. Okay, sometimes generative models like LDA and naive-Bayes are easy to fit, because the logistic regression kind of models, which is basically a discriminative model, requires minimization of some loss, and it typically tends to be a convex loss, like the log loss or the hinge loss in the SVM case. But there's an optimization, and you typically need to do that via gradient descent or stochastic gradient descent or LBGFS or one of those things. We haven't talked about optimization at all in this class, and you'll learn much more about it if you take a more advanced class, either in stats or machine learning or AM207, any one of these. But something like naive-Bayes requires absolutely no optimization. It's a really, really, really simple classifier. And something like LDA just requires you to fit Gaussians. The formulas themselves look a little bit complicated, but once you get to work with Gaussians, it's really not that complex. We can add new classes to a generative classifier without retraining it for the previous classes. Nobody said I can't do it. I have a P of C, because I had a P of x given C1 and a P of x given C2. Hey, get the Martians in. P of x given C3, whatever the heights and weights of these Martians are. If I remember seeing the movie Mars Attacks, they're much shorter, and therefore probably not much heavier either. Okay, what else? So generative classifiers can handle missing data easily, whereas the discriminative classifier, since they're trying to plot the boundary, missing data can actually shift around the boundary. And here, missing data is just, okay, we just missed out one sample in the Gaussian. Big deal. Not a big deal. Usually, if you have that kind of a strong assumption of this Gaussian, it's not going to shift so much because you had one sample less. Okay. Generative classifiers are better at handling unlabeled training data, which is semi-supervised learning and unsupervised learning, which we'll talk a little bit more about next week. Pre-processing data is generally easier with discriminative classifiers because pre-processing data, it just means that you're rescaling it, standardizing it, you're doing all of these kind of things. They don't actually change the assumptions of any kind of model. You're just trying to put a line in between somewhere or a plane in between somewhere. And then finally, discriminative classifiers generally give better calibrated probabilities because all you're actually trying to do is to get the boundary out there. You're not trying to have some complex, like weird elliptical shape that you're trying to fit, which when you change things around might actually change the boundary. So like naive Bayes, for example, all the probabilities are kind of wrong, so either they're going off in one direction. Even the boundary, whilst the boundary will remain the same, the exact contours on the sides of the boundaries, they may be steeper in some places and not so than they should have been, and so on and so forth. So and since the probabilities really depend upon the boundary in both models, and they come to the same thing, they come to the logistic regression kind of thing in naive Bayes as well as, for example, LDA. The discriminative classifiers give, in general, somewhat better probability calibrations. They're not that sensitive to the exact modeling assumptions that have to go in. Okay, so I think I'll stop here for the time being.